Today we're going to take a look at section 1.2. We started looking a little bit last time at some pattern kind of things. Gauss's stuff is sort of an example of patterns. At least we saw how it could be thought of in that way last time. We're going to look at some more kinds of patterns, or some other kinds of patterns today as well. To start with, I want to talk about what a conjecture is, because you're going to see that language used and you need to be aware of what it means. All a conjecture is it is a statement or conclusion that hasn't been proven. So it's like you looking at something and saying, this is what I think is happening. That's a conjecture. It's your interpretation of what's going to happen next in the problem, or what the pattern is for the problem. We're new a lot with patterns, so I mentioned that one. But it's your best guess of what's happening next. It's not something that you've proven yet. There are two different types of reasoning. There's inductive reasoning and there's deductive reasoning. Inductive reasoning is a method of making generalizations based on patterns. So, for instance, this would be like me telling you that I have a paper, and this is actually true, I have a paper in my house on my fridge that says, on Monday, my children eat cereal for breakfast, on Tuesday they have eggs, and on Wednesday they have oatmeal. Okay? And then, based on this piece of paper being on the side of my door and me telling you that if you show up at my house on Tuesday, your conjecture is that I'm having eggs for breakfast. Okay? So this is showing a pattern, me writing down this pattern, you making a claim of what you think is going to happen based on what the pattern has been. Now, you may show up on Tuesday and I'm out of eggs and it really doesn't end up happening to be eggs, right? But that's a conjecture that you've made based on what's been done in the past. So, that's inductive reasoning. Deductive reasoning is the use of mathematical axioms, theorems, definitions to decide what's going to happen next. And I'll show you some examples of how that one works a little bit more concretely when we encounter it, okay? But one example that you would use is, let's say you were given an equation of something, like an equation of a line, and you wanted to know what is the y value when x equals 7. Well, this would be an equation, which means you could take that x value of 7 and you could plug it into the equation of the line, and you could automatically get out an answer of what y is based on an equation that you were given, instead of maybe a list of numbers and you're just speculating. Okay? A counterexample is, and we're going to keep using counterexample throughout the class. We've seen them, you've seen them a lot before. Is a counterexample just shows something that is actually false. For example, there really is this thing on my door, or my side of my fridge, that says that this morning my children were supposed to have oatmeal or fruit bars. Well, it was the first day of school, and my son isn't especially fond of either of those options. And so he asked me very sweetly this morning if he could have cereal. That'd be a counterexample, because I let him have cereal this morning instead of having oatmeal or a fruit bar. Okay, so counterexample is just showing that whatever the pattern was established, or whatever you thought was going to happen or be true, doesn't always work. All right? Sequences is where we're going to start taking a look at these patterns. A sequence is an ordered arrangement of numbers, figures, or objects. Kids start working with sequences very early. They do it a lot with shapes and colors to start with. So you might see in a pre-K classroom them being given something where it has circle, square, and the question is, what comes next, right? Or they might throw something in there with color where it's, red circle, blue square, what comes next? Now they have to identify both the shape and the color. So that's something that would happen in terms of shapes or figures. We're going to do some stuff with numbers as well. We're going to do some stuff with figures, but the numbers is going to be our primary focus in this particular section of material. The first type of sequence that we're going to encounter in terms of numbers is going to be an arithmetic sequence. An arithmetic sequence is a sequence where you get from one term to the next term by adding the same value every time. Now, you guys saw some of that in the last section when we did Gauss's stuff. Right? You added the number 1 every time to get to the next term. Or, like the one that you guys gave me the example of, you added the number 2 every time. And then I created a sequence on the board where I added the number 3 every time. Okay? Those were all arithmetic sequences. I add the same number to get the next term. Right? The number that you add every time to get the next term is called the common difference. And I know difference makes it sound like subtraction. The reality is you don't have to add a positive number every time. You could be adding a negative number or subtracting every time too. So let me just kind of write down an example here so that you have a spot in your notes where you've written down an example. We could do 2, 4, 6, 8, 10, and so on. Because to get from term 1, that is the number 2 here, to the second place, the 4, I would have to add the number 2. And to get from 4 to 6, I would add the number 2, and so forth. Okay? So this would be an arithmetic sequence. But likewise, we could add a negative or subtract a value, and it would work as well. So I could start with, say, 100, and then do 97, and then 94, and then 91. And if I were doing this, the common difference would actually be what value? Negative 3. So the common difference doesn't have to be a positive number. It could be a negative number. So this one here, the common difference, I'm going to call it D, just so that I can write it down, was 2. Here the common difference, D, is actually a negative number. It's negative 3. Now what we're going to do is we're going to take a look. Oh, I'm sorry, we're not quite there yet. I need to talk about a little bit more about some sequences before we get to my examples. All right. A recursive formula is a formula that's based on the pattern, but you actually have to know where you start in order for it to work. So this is actually telling you you've got a pattern, and after one or more consecutive terms, the rule is given on how to obtain the next term. So you guys are actually creating, in your mind, a recursive definition when you were saying, I add 2, I subtract 3. That's a recursive way of thinking about this sequence. What do I do to get the next one? And recursive formulas are great if you just want to know what do I do to get the next term or the next 3 terms. The problem is that what happens if somebody says, what about the 50th term? Well, unless you want to do kind of like what Devin was describing when she was counting things, unless you want to write them all out to get to the 50th term, this recursive kind of an idea, it doesn't really give you a lot of help. And the 50th term you might be able to write out, but what if they want the 651st term? I don't want to write them out until I get to 651 terms, right? So there's got to be another option as well. So recursive formulas have the ability to just describe it in a way that tells you what happens next. The nth term actually establishes a formula or an equation that allows you to find any term you want. So instead of worrying about what happens next and only be able to get the next term, you can get the 651st term just like this because you have an equation or a formula that you're using instead. Okay? So that's definitely a benefit to being able to have that. I want to throw in one of these because I think it's interesting, and it is not an arithmetic sequence. It's a Fibonacci sequence. A Fibonacci sequence has a very interesting pattern. Now, you may look at this and you may not even see a pattern to begin with, and some of you may have seen these before. But a Fibonacci sequence has the pattern that if you add the first 2 numbers together, you get the third one. And if you add the second 2 together, right, 1 and 2 here, you get 3. And if you add 2 and 3, you get 5. If you add 3 and 5, you get 8. 5 and 8, you get 13. So if you're looking at this Fibonacci sequence, there is not an nth term formula. It is only defined in a recursive way. Okay? So if you take a look at this, however, this recursive idea, you can continue this sequence for the next 3 terms or whatever. Let's do the next 3 terms. What would come after 21? 34, right? Because I add 13 and 21 together. What would come after 34? 55. And we get that by adding 21 and 34. What will come after 55? 89. Okay. So this is a Fibonacci sequence. Fibonacci sequences occur in nature a lot. You see them on rings of trees. You see them on the shells, like the snail shells that continue to grow as the snails, get larger, the snail shells. You see them in some flower patterns and things like that as well. So Fibonacci sequences are actually quite common in nature. All right, the third type of sequence we're going to talk about in this section is called a geometric sequence. Okay, arithmetic, we added a value every time, add or subtract, depending on how your perspective is on that, right? With a geometric sequence, we multiply by a value to get from one term to the next. The value that we multiply by is called the common ratio. Okay, I'll do the definition here of a sub n in a moment here, but let me give you an example of these geometric sequence with the common ratio. An example of this would be the values 2, 4, 8, 16, 32, 64, so on. Instead of adding 2, I mean, I can add 2 to get from 2 to 4, but then it won't work to get from 4 to 8, right? It's not the same value. But if I multiply 2 by 2, I get 4. And I multiply 4 by 2, I get 8. And I multiply 8 by 2, I get 16. So I'm multiplying by the same term every time instead. And again, it doesn't have to be a term that's positive. It could be a negative that you're multiplying by every time. That's okay. It also could be a fraction. I mean, like, it could be the value 1/2. And so it actually looks like the values get smaller, or they turn into fractions instead of saying as whole numbers. That works too. But a common ratio here, so I'll call it R, here would be the number 2. It's the number that I multiply by every time. Definition of a sub n. And I'll show you why here we need this in a minute, but for the now. If n is a natural number and you have a raised to the nth power, all that means is that you multiply the value a by itself n times. If n is 0 and your a value is not 0, then a raised to the 0 power is 1. For the moment, we'll take that by definition. In Math 2, we actually show why that works and why that's true. And we'll talk more about this idea of exponents, this a sub n, a to the n rather, when we get into chapter 3, I think it is, as well. We need it here because what we're going to be doing here in a moment is we're going to take some sequences on the next slide, and we're going to decide, are they arithmetic, are they geometric, are they neither? We're going to do that. And we're going to list the next few terms, all right? But even though it doesn't say it on this slide, the other thing we're going to do on this slide is we're going to create that general term, that int term that I talked about, because you do have some examples in your homework that ask you to do that, and I failed to include one on your slides. Okay? So if you will, just add sort of a piece into this description up here that says, and find the nth term. Find the formula for the nth term or something like that. All right, so the first things we're going to do are the ones that are printed, though they're in blue on the screen. So the first one, 1, 4, 7, 10. How do I get from one number to the next? Add 3. Because I add 3, what kind of a sequence is this? Arithmetic. Excellent. Now, if I wanted to, oh, then it says list 3 terms that continue the sequence. So we're going to list the next 3 terms. So what comes after 10? 13. And then? And then? 19. Excellent. So we've done all of the directions that are actually printed in your notes now, right? What I want to show you is I want to show you how to create the nth term, because some of the time it'll say find the nth term, or it might just simply tell you something like find the 561st term. And you don't want to write them out. Okay? So if either of those kinds of directions happen, you would need to find that formula to make that a reasonable thing to find. So how do you do that? Well, the value that we add every time, think about back to elementary school. Somewhere along the way in elementary school, probably somewhere between 2nd and 3rd grade in there, somebody said to you, what if you want to add something together, something a bunch of times? What if you want to add 3 plus 3 plus 3 plus 3 plus 3 plus 3 7 times? Got to be a simpler way to do it. What do? You learn to multiply, right? That's sort of the beginnings of why we talk about multiplication, is because we don't want to do this repeated addition that many times. So that's what we're going to do here. What is the number that we are adding here multiple times? 3. So my nth term is going to have a 3 in it. And that 3 is going to be multiplied by n. Because every time I increase the sequence, that is, every time that I go to the next term, I add 3 more. I repeatedly add 3, and that's multiplication. Now, what we need to do, though, is that this is probably, for the most part, not going to be the exact formula you need. But you're so close. And there's equations I could give you to make you memorize, which I think are fine, but I don't think that's terribly helpful. So what I want you to do is to see how to create the rest of this on your own, because it's not hard. 3n doesn't work, because if I put in n equal to 1, what do I get? 3. Is 3 the first term in my sequence? No, it isn't. But if I add or subtract something, I could get the first term in my sequence. I'm going to subtract 2. Why 2? Because that's what it would take to get me the value of 1. All I'm going to do at the end of that, okay, so the common difference that I just got, the 3, is multiplied by n. It always happens that way. And then I'm going to add or subtract whatever I need to get the first term. So now if I plug in the n equal to 1 here, I get 3 times 1, which is 3, minus 2, which is, and is that my first term? It is. Let's say I put in n equal to 2, just to make sure that I did it right. 3 times 2 is 6. Minus 2 is that my second term? It is. And I could keep going, and it would give me my third term as 7, and my fourth term as 10. Okay, it always works that way. Whatever value you need to add or subtract on the n is found by actually trying to put the value n equal to 1 in and comparing it to the first term in your sequence. Okay? All right, let's try the second one. 3, 6, 12, 24. What do I have to do to get from one term to the next on this one?
Multiply by 2.
Yep, multiply by 2. Okay, which means what kind of a sequence is it? This is geometric, okay, because I'm multiplying by 2. It has a common ratio of 2, right? And we're going to find the next 3 terms. So what comes after 24? 48. And then? 96. And then? 192. Geometric sequences get large quickly, so you have to be a little bit careful. Now, the way I did the nth term in the last one won't work for this one, because I'm not adding the same number every time, I'm multiplying. So, think with me again, back to grade school, a little further along. Somewhere along the way somebody said, what if I want to multiply 3 times 3 times 3 times 3 times 3? You get exponents. And that's why we had this definition of exponents on the previous slide. Okay, so when you repeatedly multiply, that creates an exponent. So we take the value we repeatedly multiply by. So here's my nth term process now. The value I'm multiplying by becomes the base of an exponent. Now I'm going to have to explain to you why I'm about to do what I'm about to do, but the exponent's actually n minus 1, so just bear with me for a moment and put the n minus 1 there. And notice then, well, let me tell you why I'm putting the n minus 1 there. Notice here that if I put in n equal to 1, what happens to the exponent? I get 0. And what is 2 raised to the 0 power? 1. That was on the previous slide, right? So if I actually put in the exponent of 1, putting the n equal to 1 into the exponent, this whole thing that I've written so far becomes the number 1. Agreed? And here's why that's helpful. Because what that means I can do in front of this 2 to the n minus 1 is I can simply write my first term, 3. Because when I put in n equal to 1, the exponent becomes 0. The 2 to the 0 goes away, and I'm left with the 3. So I get my first term. And you can check to see that it works by trying the number 2. What happens when I plug the number 2 in here? 2 minus 1 is 1. 2 to the 1 is 2 times 3 is 6. And that was your second term. Just for fun kicks, let's try the third one, okay? If I put in 3, 3 minus 1 is, 2 squared is, times 3 is, and that's it too, right? So this pattern always works. The exponent's always n minus 1. The base of it is always the common ratio. In this case, it was 2. And the value in front is always the first term. It's actually a little bit easier to create than the other one because you don't have to trial and error to get the plus or minus at the end. It's automatic. All right, the question is asking you, is this inductive or deductive reasoning? I'm starting out with a list of things and I'm creating what I think is going to happen next. What kind of reasoning is that? That is inductive reasoning. Okay, go back to the definitions just to remind ourselves. Inductive reasoning is making a generalization or predicting the future based on the current pieces of information. Yeah, this is what the weathermen do all the time, right? Okay, so predicting the weather is inductive reasoning. Looking backwards at history, that's deductive because it's already happened and we can talk about that. All right, so inductive reasoning on this pattern that we just did. All right, another example. On this example, we are given equations. And we're asked to find the first 5 terms in the sequence and decide if the sequence is arithmetic, geometric, or neither. So, we're going to plug in the number n equal 1, and then equal 2, n equal 3, and so forth. And we're going to do it for the first 5 terms, and we're going to write those down. So if n equals to 1, what do I get? 11. And then what? Okay, and n equal to 3? N equal to 4? And n equal to 5? 31. Okay, so that's the first part of the directions. Second part of directions says to decide, is this arithmetic, geometric, or neither? It's arithmetic. How did you decide? Because there's a couple of ways you could have.
You look at the equation, put the nth term.
Good. You looked at the equation. All right, so the equation, 5n plus 6. That's an arithmetic equation, right? The last one I created was 3n minus 2. They all look the same. If you're given an equation, you can tell if it's arithmetic or geometric by the equation. That's one way anyway, right? So I've got some number times n plus or minus something else. You can decide another way too. What if you weren't actually given the equation and you were looking at the 11, 16, 21, 26? You can add 5 every time, right? Yeah, this sequence adds 5 every time, so it's arithmetic for that reason as well. Part B, n squared minus 1. All right, so what happens when n equals to 1? Zero, right? 1 squared is 1 minus 1. Okay. How about n equal to 2? 3. N equal to 3? N equal to 4? And n equal to 5? Okay, good. Those are the right values. Is this arithmetic, geometric, or neither? Is it? This one's neither. Let's make the decision first based on the sequence that we created. 0, 3, 5, 8, 15, 24. It's not arithmetic because you're not adding the same value every time, right? It's not geometric either because you're not multiplying by anything. In fact, the fact that there's a 0 in it automatically excludes the possibility that it's even geometric because I can't multiply 0 by anything to get you something that's not 0. So it's not geometric for that. Let's go back to the equation. Why is the equation not geometric? Yeah, the n is actually the base on this problem, not the exponent. Do you see the difference? Mm-hmm. This formula over here that I created, 3 times 2 to the n minus 1, the exponent has the n in it, not the base. Okay, so it doesn't have that same pattern. The other thing about geometric that you might notice is that if there's any subtraction, and there is, it's in the exponent, right? Mm-hmm. It's not on the baseline itself, and this also had that feature where the minus 1 was actually after the squaring and everything was going on, and that doesn't happen for geometric either. Question, is this inductive or deductive reasoning? This is deductive. Okay, so it tells you over here again, deductive reasoning is having a mathematical axiom, theorem, or definition, in this case an equation, right? That is what this is, it's an axiom, and assumed to be true, undefined terms, assumed to be true, and logic for proof. So you're making a decision based on something that has a formula to use. And so this one is deductive reasoning. Okay. Number 3. The last sort of thing on that slide that I just moved away from the earliest on, had the phrase or the word counterexample. And a counterexample is an example showing something to be false. So this question says to find a counterexample for the following. If n is a natural number, then n plus 5 over 5 equals n plus 1. So the first question I want to ask you is, why might a student think that this is true? Yeah. They might be looking at this and doing something like that, right? But you can't do that. That's true. But it doesn't work very well if a student tries that and you just say you can't do it.
Well, because you have to explain why.
Yes, you would have to explain why. And one way to explain why is to use counterexamples. Counterexamples are great because they give you the basis to be able to tell a kid who doesn't have the mathematical background that you do why in a way that they can understand. Okay? So you're creating an example that shows them it really doesn't work, and here's some numbers that tell you why. All right, now the nice thing about counterexamples is that usually when something's false, you can create a lot of different things to show it's false. It's a lot more difficult if something's true because you can't test every possibility to show that something's actually true. But usually there's lots of examples that show something's false. So I want you to create an example or create a number for me. Give me a value for n, and we will see if we have a value that won't work. 5. Okay. Kirian, give me a number 5. So we're going to test both sides. We're going to try n plus 5 over 5, and we're going to try 5 plus 1. And the question we want to know is, are they equal? Oh, I'm sorry, I left that out. 5 plus 5. Get it in there. 5 plus 5 over 5. All right, so 5 plus 5 is 10. So we've got 10 over 5 on the left. And then 10 over 5 is 2. Good. On the right, I have 5 plus 1, which is 6. And I'm pretty sure at this point, the child that's working with you is going to see that these aren't going to be the same, which means that that process of canceling didn't work. Now, they may want to talk to you about why it didn't work, and you can go on from there. This question doesn't ask you that in particular. But this definitely at least verifies to them that you know what you're talking about because you showed them one case where it didn't work. And the reality is you could show them lots of cases. So if they're just like, but maybe it works, other examples, well, maybe it does. Let's try one. And pretty soon you're going to try a whole bunch, and they're all going to not work. You may randomly try something that does, but most of the time they're not going to work.
But
yeah.
The reason you can't is because the n plus 5 is together, right?
Yes, the
Only
reason
way
you
could
can't.
cross it off is if the bottom also said n plus 5.
Yeah, the reason you can't is because of the addition. The addition is occurring, and so in essence, in terms of order of operations, what you've really got here is you've got a parentheses that actually forces you to add those pieces together before you do the division. Yeah. The other thing that you can talk about, and we talk about this when we talk about fractions, is that what we really have here is we have n over 5 plus 5 over 5. Right? Each of those pieces individually are over 5. So yes, the 5 over 5 cancels to 1, but the n is still over the number 5. So that process doesn't work as well. Yeah. Okay, let's take a look at another sequencing thing that is not numbers. It has a number component to it, but this is not numbers. Figurate numbers. Figurate numbers are based on geometric patterns, and they don't even have to have dots necessarily, but they're a pattern issue. This one we're going to do has dots. And they're neither arithmetic nor geometric, but dots can be used, or you can use straight line segments or things like that. The ones we're looking at are dots. Dots can be arranged in the shape of certain geometric figures. So this one right here is called a triangular number. I have 1 dot, and then I have 3 dots making up a triangle, and I have 4 dots, I'm sorry, not 4 dots, but I have 6 dots making up a triangle, and then 10 dots making up a triangle, and so forth. So on this one, can you imagine what you would do to find the next term? And what visually is happening? Don't think in terms of numbers. What visually is happening? Are we just adding a dot on the bottom? Row of dots, right. So we're going to add a row of dots on the bottom, and the number of dots is going to have 1 more than it did before. Yeah, which is where you're adding the dot business was. Yeah. So we're not just going to add 1 dot. We're going to add a whole new row of dots. And the new row of dots is going to have 1 more than the last row did. Okay? So can we create the next 3 images if we needed to? Certainly. We can also then look at these particular numbers, 1, 3, 6, 15, or 10, 15. And we can recognize that while it isn't arithmetic, there is a pattern. So take a look. 1 to 3 is adding 2, right? What is 3 to 6? Adding 3. What is 6 to 10?
4.
Adding 4. And 10 to 15? Adding 5. So we could also establish this kind of a pattern and say, what's next? Now again, I don't have a closed form, like an equation that I can write when I'm doing this, but I can see a pattern. I want to show you something else that happens in this. Let me write down a couple more of them. So what would come next?
21.
Yeah, I'd add a 6 and I'd get 21, and then 28, add a 7 and get 28. All right, what we're doing when we're looking at what did I add to get the next term, this process actually here has a name. It's called first differences. All it is it's the first time I did it, right? And I'm looking at the difference between the numbers. I'm writing it as addition because I'm moving from left to right. But I'm just writing down what is the difference between these values. Let's take a look and let's do it again. I can go from 2 to 3. And what do I get? Plus 1, right? The difference between 2 and 3. So consider 2, 3, 4. Consider the ones that I wrote down in that first differences line as though it's the sequence itself. How do I get from 2 to 3? I add 1. How do I get from 3 to 4? I add 1. How do I get from 4 to 5? 5 to 6. And 6 to 7. That is an arithmetic sequence then, right? So it didn't work on the first differences. It wasn't arithmetic as it started out. The first differences didn't have the same value. However, this second time I did it, affectionately called the second differences, it did work, didn't it? So you're going to have a couple of examples in your homework where the first time you do the differences, they're not going to look like you're going to see anything helpful. This one actually looked pretty helpful the first time, right? I mean, like you saw the pattern. It wasn't the same number, but you saw the pattern that was being created. You're going to have a couple in your homework where you're not even going to see the pattern the first time you do the first differences. Do the second differences and see what happens. And you know what? If you don't see a pattern in the second differences, what can you do? You can do the third differences, and you can see what happens. I don't think you have to get down to the fourth differences on any of them. I think you'll see a pattern before you get there. But at some point, you're going to start recognizing a pattern. And if you go down far enough, you will see that the underpinning of the final line that you do will be an arithmetic sequence at some point. Yes?
So once we get down to arithmetic sequence, the whole thing is arithmetic.
No, the whole thing's not arithmetic. No, this isn't an arithmetic sequence, but it has some relationship to it. Like, I mean, there's some similarities, right? And I can use the fact that it is arithmetic in at the very last part of it's arithmetic to work my way back up to find something else. Like, for instance, you guys don't need this on this particular problem, but let's say you looked at 2, 3, 4, 5, 6, 7, and you didn't see a pattern. I mean, you do, but there's going to be somewhere the first time you do it, you don't see a pattern. Well, you can use the fact that the second line or the third line has a pattern to work your way back up. So let me show you what I mean by that. Let's say that we stopped right here. And you said, okay, I don't see the pattern between 2, 3, 4, and 5. Again, bear with me, pretend for a moment. But you knew if you did it again, you've got all these plus ones. Well, you can say, well, I can take this and I can go plus 1, and I can say, okay, what is 5 plus 1? Well, that's 6. And then I can say, okay, there's the number 6, and now I can take the last term, which was 15, and I can add 6 to get 21. And you could do it again. You could say, okay, the common difference down here, that's the number 1, and I can take the last term 6, I can add 1 to it, and I can get 7, and then, oops, sorry, that was just supposed to be 7 there. And then I can go up again, and I can say 21 plus my 7 is 28. So you can sort of work your way back up in sort of a tree kind of a pattern.
But you'll never have it to where you just have the bottom row and you have to work yourself up to the very...
No, you'll always start with the top. Yeah.
They'll always give you examples of like all three if you had to work back.
They wouldn't give you the example of all three. You'd create them. So they would give you the problem like 1, 3, 6, 10, 15, and you would do the first differences, and you'd do the second differences, and you might need to do a third difference. But at some point, you're going to recognize a pattern.
But they wouldn't give you like second differences with nothing else and say,
no.
find out the pattern.
No, they wouldn't. All right. Square numbers. Let's pick back up here this next time. We'll do square numbers in our last slide. And next time we will actually move on into section 1.3 maybe briefly, and we'll have a ton of time for group work too. So make sure if you don't have already your 1.3 notes printed off, have 1.3 printed off. I know it doesn't say we're going to, but this way will give us more time in review and questions at the end and stuff. And you'll still have a substantial amount of time next time to do practice on these problems. Just like section 1.1, problems in the entire chapter 1 are going to take you a while. That's not going to be true throughout the whole semester, but it will be true for chapter 1, okay?